Have you ever wondered, if concrete is so strong, why almost every structure still uses steel reinforcement? I'm Sonny Corner, an engineering enthusiast. I enjoy exploring things that look ordinary but are actually pretty fascinating. If that sounds interesting to you, feel free to follow the channel.
Concrete looks hard, really hard. When you touch it, it feels solid, heavy, permanent. It's the kind of material people instinctively trust. We build houses with it, bridges, parking garages, highways, even nuclear plants. So here's a question that sounds almost stupid at first, but really isn't. If concrete is already this strong, why do we bother putting steel inside it? Not just a little steel, sometimes a lot of it. Dense steel cages, tightly packed, completely hidden once the concrete is poured. If concrete can hold up entire buildings on its own, what's all that steel really doing in there? Most people never think about this, and honestly, why would they? Concrete does its job quietly. It just sits there, year after year, not moving, not complaining. As long as nothing goes wrong, nobody questions it. But the interesting part is this: the moments when concrete fails are almost never the moments people expect. It's rarely about weight alone. It's not just too heavy so it collapsed. Instead, cracks appear, small at first. Hairline cracks you might barely notice on a ceiling, a beam, or a slab. And once cracks show up, people start asking questions. That's usually when engineers get called in. What many people don't realize is that concrete has a very specific personality. It's strong in one very particular way and surprisingly weak in another. Concrete is excellent at being squeezed. It handles compression extremely well. You can stack enormous amounts of weight on top of it, and it barely complains. That's why columns work. That's why foundations work. That's why ancient stone structures are still standing today. But here's the part that feels counterintuitive. Concrete is terrible at being pulled. It doesn't like being tensioned at all. And buildings are being pulled on constantly, whether we notice it or not. Take a simple concrete floor slab. When people walk on it, when furniture is placed on it, when cars drive over it, the slab doesn't just sit there. It bends. Not much, but enough. That bending creates two very different zones inside the concrete. One side gets compressed, the other gets stretched. And concrete hates being stretched. That stretching is where cracks are born. You can try a simple thought experiment. Imagine holding a piece of chalk. Press straight down on it. It holds up surprisingly well. Now grab both ends and try to pull it apart. It snaps almost immediately. Concrete behaves in a very similar way. This is why saying concrete is strong is only half the truth. It's strong in compression, but fragile in tension. And buildings don't just experience one type of force. They deal with bending, vibration, temperature changes, wind, traffic, people moving. Even gravity itself creates bending forces in floors and beams. So the real question becomes, if concrete is weak where structures are constantly being pulled, how do we deal with that weakness? This is where steel quietly enters the picture. Steel is almost the opposite of concrete in this respect. It doesn't mind being pulled. In fact, it's very good at it. Steel can stretch slightly without breaking. It can absorb tension and keep working. That flexibility is incredibly valuable. So instead of asking, why do we add steel to concrete? A better question might be, why would we rely on concrete alone knowing where it's weak? Steel isn't there to make concrete harder. That's a common misconception. Concrete is already hard enough. Steel is there to handle what concrete simply can't. When steel is placed inside concrete, it sits exactly where tension is expected to happen. As the concrete tries to crack under tension, the steel steps in and takes over that job. The concrete presses, the steel pulls. Each material does what it's good at. That's the real reason this combination works so well. And there's another subtle point people rarely notice. Concrete and steel actually work well together physically. They expand and contract at very similar rates when temperatures change. That means they don't fight each other as the weather gets hot or cold. They move together. Once the concrete hardens around the steel, the two materials become locked into a single system. You don't see the steel, you don't think about it, but it's always there quietly carrying the forces that would otherwise tear the concrete apart. So when you look at a concrete structure and think, this thing is solid, it's not going anywhere, you're partly right. But what really makes it reliable isn't just the concrete you see, it's the steel you don't. And that's the part most people walk past every day without ever realizing how important it is.
To really understand why concrete needs steel, you have to stop thinking of strength as a single thing. Most people hear the word strong and imagine one simple idea, something that doesn't break. But in the real world, strength comes in different forms, and concrete is a perfect example of that. Concrete is incredibly good at one thing and surprisingly bad at another. It handles compression beautifully, but it struggles the moment tension enters the picture. Compression is easy to visualize. It's the force that pushes things together. If you place a heavy object on a concrete block, the concrete is being squeezed. That kind of force is where concrete shines. You can stack enormous weight on it, and as long as it's evenly distributed, the concrete barely reacts. This is why columns work so well. This is why foundations can carry entire buildings. This is why ancient stone structures, built long before modern engineering, are still standing. Stone, brick, concrete, they all love compression. They're happiest when something is pressing down on them. But tension is a completely different story. Tension pulls things apart. Instead of being squeezed, the material is being stretched. And concrete hates being stretched. It doesn't stretch gracefully. It doesn't give warnings. It doesn't slowly deform and recover. It cracks. And once concrete cracks, it loses a big part of what made it reliable in the first place. What makes this tricky is that most structures experience tension all the time, even when they look perfectly still. Take a concrete floor slab. At a glance, it looks flat and unmoving. But the moment people walk on it, the moment furniture is placed on it, the moment gravity does what gravity always does, that slab starts to bend. Not enough for you to notice with your eyes, but enough for the forces inside the concrete to change. When a slab bends, something interesting happens. One side gets compressed, the opposite side gets stretched. The compressed side is fine, concrete is comfortable there, but the stretched side is under tension, and that's where problems begin. This is why cracks almost always appear on specific surfaces. Ceiling cracks, cracks at the bottom of beams, cracks along the underside of balconies. Those are not random. They are visual clues that tension has exceeded what concrete can handle. And here's the part that surprises a lot of people. Concrete doesn't need much tension to fail. Compared to how much compression it can take, its tolerance for tension is extremely low. That imbalance is the key. Concrete might handle massive weight pushing down on it, but a relatively small pulling force can cause it to crack. You can think of it like a dry cookie. Press straight down on it and it might survive. Try to bend it slightly and it snaps. That doesn't mean the cookie is weak. It just means it's strong in one way and weak in another. Concrete is the same. Now add real-world conditions into the mix. Buildings don't just deal with static weight. They deal with movement. People walking, cars driving, wind pushing, temperature changing. Concrete expands when it gets warm. It contracts when it cools. Those tiny movements introduce tension again and again, day after day, year after year. Each cycle is small, almost invisible, but concrete remembers. Microcracks form. They slowly grow, and eventually they connect. This is why cracks often appear years after construction, not immediately. It's not because something suddenly went wrong. It's because tension has been quietly doing its work all along. And once cracks exist, new problems follow. Water finds its way in, moisture reaches deeper layers, chemical reactions begin.
The structure hasn't collapsed, but its long-term reliability has already changed. All of this traces back to one simple fact. Concrete is not designed to resist tension on its own. It was never meant to. This isn't a flaw in concrete, it's just the nature of the material. In fact, if you tried to design a structure that avoids tension completely, you'd end up with shapes that are impractical for modern life. Arches, massive walls, very limited spans. That worked thousands of years ago. It doesn't work for parking garages, high-rise buildings, or long bridges. Modern structures need to span large distances. They need open spaces. They need flat floors and wide decks. All of those features introduce bending, and bending introduces tension. So once you accept that tension is inevitable, the real question becomes, how do we deal with it? You have two options. Either you can try to make concrete handle tension on its own, which means making everything absurdly thick and heavy, or you can accept concrete's weakness and bring in something that naturally handles tension well. That's the turning point. Not how do we make concrete stronger, but how do we support concrete where it's weak? Understanding this changes how you see structures. When you look at a crack, you stop thinking of it as a mystery, you start seeing it as evidence. Evidence of where tension lived, evidence of how forces moved through the structure. Concrete didn't fail because it was poorly made, it failed because it was asked to do something it isn't good at. And that realization sets up the next step perfectly. If concrete is strong under compression and weak under tension, then the solution isn't complicated. You don't fight the material, you work with it. And that's exactly why steel becomes inevitable.
Once you understand that concrete struggles with tension, steel suddenly makes sense. Not as an extra, not as insurance, but as a partner. Steel and concrete aren't mixed together by accident. They solve each other's problems almost perfectly. Steel is very good at tension. You can pull on it, stretch it, bend it, and instead of cracking, it resists. More importantly, it resists in a predictable way. Steel doesn't suddenly fail the moment tension appears. It stretches first. It gives warning. It absorbs energy. That behavior is exactly what concrete lacks. So when you place steel inside concrete, you're not making concrete stronger in a general sense. You're assigning jobs. Concrete handles compression. Steel handles tension. Each material does what it's naturally good at. Think of a concrete beam spanning between two supports. From the outside, it looks simple, just a solid block. But inside that beam, forces are constantly moving. The top part of the beam is being squeezed. The bottom part is being pulled apart. Compression above, tension below. Concrete is perfectly happy at the top, no problem there. But at the bottom, tension is unavoidable, and that's where steel steps in. The steel bars placed near the bottom of the beam are not randomly located. They sit exactly where tension is expected to appear. When the beam bends, the steel stretches slightly and takes the load, while the surrounding concrete holds it in place. They move together. This cooperation is the key idea. Steel alone would bend too much. Concrete alone would crack. Together, they behave like a single system. What makes this partnership even more effective is something most people never think about. Steel and concrete expand and contract at almost the same rate when temperatures change. That's not common. Many materials fight each other as temperatures rise and fall. They separate, they loosen, they break bonds. Steel and concrete don't. When the sun heats a structure during the day, both materials expand together. When temperatures drop at night, they contract together. That shared movement keeps them bonded year after year. This is one of those quiet details that makes reinforced concrete so reliable. Another detail that matters is grip. Concrete doesn't just surround steel passively, it grabs onto it. The surface of steel reinforcement isn't smooth. Those ribs and ridges you see aren't for decoration.
They create mechanical interlock. When steel tries to slide under tension, the concrete resists that movement. Force transfers from one material to the other, not suddenly, but gradually along the length of the bar. This smooth transfer of force prevents sudden failures. It's also why cracks, when they do appear, are often thin and distributed instead of one large catastrophic break. Steel doesn't stop cracks from forming entirely. That's a common misunderstanding. Cracks are expected. What steel does is control them. Instead of one big crack, you get many small ones. Instead of sudden collapse, you get gradual deformation. That difference is everything in real structures. It gives engineers time. It gives occupants warning. It gives structures resilience. Now, zoom out a bit. This idea doesn't just apply to beams. It applies to slabs, columns, walls, foundations. Anywhere tension appears, steel quietly takes over. In columns, steel helps deal with imperfections and bending. In slabs, it carries tension caused by people, furniture, and vehicles. In walls, it resists temperature movement and shrinkage. Reinforced concrete isn't about brute strength, it's about balance. One material doing everything poorly is far worse than two materials each doing one thing well. This is why reinforced concrete changed the world. Before it, structures had limits. Spans were short, walls were thick, open space was expensive. Steel alone allowed long spans, but required fire protection and complex fabrication. Concrete alone was durable, but restrictive. Together, they unlocked something new. Tall buildings, long bridges, wide parking garages, simple, repeatable construction. And once you see this partnership clearly, you start noticing it everywhere. You stop asking, why is there steel inside concrete? You start asking, where is tension hiding in this structure? Because wherever tension exists, steel is probably already there, quietly doing its job. This also explains why removing or cutting reinforcement is so dangerous. From the outside, nothing seems to change. The concrete is still there, the structure still looks solid. But inside, the system has lost its balance. Concrete is suddenly being asked to resist tension again, and it never learned how. This isn't about rules or codes, it's about respecting materials. Steel doesn't make concrete invincible. Concrete doesn't protect steel from everything, but together they create something far more reliable than either could achieve alone. And that idea goes far beyond construction. It's not about forcing one material to cover every weakness. It's about recognizing limitations and designing around them. Concrete accepts that it will crack under tension. Steel accepts that it needs support to stay in place. Neither pretends to be perfect. That honesty is what makes the system work. Once you understand this, reinforced concrete stops feeling like a technical solution. It feels like a very human one. Know your strengths, know your weaknesses, and don't try to do everything alone.
By now, you probably have a sense of concrete's personality. It's strong under compression, it cracks under tension, it's predictable in one direction and stubborn in the other. So what does steel really do inside concrete? What problem is it solving that concrete alone simply can't? The answer is surprisingly simple: tension. Concrete is fantastic at holding weight down. It's terrible at resisting forces that pull it apart. Steel, on the other hand, is almost the opposite. It handles pulling, stretching, bending, forces that would tear concrete to pieces. When engineers place steel reinforcement in a beam, slab, or column, they're not just making the concrete stronger, they're acknowledging a weakness and deliberately solving it. Steel carries the load that concrete refuses to take. Think about a concrete beam spanning between two supports. From the top, it's under compression. From the bottom, tension. Concrete thrives at the top, cracks immediately at the bottom. Steel sits where the tension will be,
quietly resisting the pull. Without steel, that beam might hold for a short while, but eventually cracks grow and structural integrity declines. It's not magic, it's complementary action. Each material has a role, and each role is clear. Concrete presses, steel pulls. Together, they behave like a single, balanced system. And there's more to it than just pulling and pressing. Steel also prevents small cracks from spreading uncontrollably. It distributes stress along its length, rather than letting one weak spot fail catastrophically. Think of it as tension insurance. Cracks can form, yes, but they won't immediately destroy the structure. The steel carries the tension, bridging the gaps that concrete can't. You can even see this in everyday structures. Walk across a concrete bridge or park on a slab, and every step you take creates tiny tension forces. Each of those forces is quietly handled by steel reinforcement without anyone noticing. The concrete alone wouldn't survive long under these repeated pulls, but with steel inside, the structure remains stable, safe, and long-lasting. Now, this isn't about covering up mistakes in construction. It's about respecting the natural limits of materials. Concrete doesn't pretend to handle tension. Steel doesn't pretend to handle compression alone. Together, they form a system where each compensates for the other's weaknesses. This is what engineers call reinforced concrete. And it's more than just a construction term. It's an idea of balance. Let's take it one step further. Steel also adapts to dynamic forces, not just static ones. Buildings and bridges are not perfectly still. Wind, vibration, traffic, thermal expansion, all of these introduce forces that shift tension around. Concrete doesn't respond gracefully to these repeated pulls. Steel does. It stretches slightly, absorbs energy, and prevents catastrophic cracking. It turns unpredictable tension into manageable stress. Another thing people rarely notice, steel and concrete expand and contract at nearly the same rate with temperature changes. Why does that matter? Because if they expanded at different rates, the bond between them would fail. The concrete could crack, the steel could slip, and the system would lose integrity. But their natural compatibility makes the composite material remarkably reliable over decades, even centuries. And here's a subtle but important point. Steel placement isn't random. Engineers calculate exactly where tension is expected to occur. They place steel precisely at those locations. In beams, it's at the bottom. In columns, it's often distributed around the perimeter. In slabs, it may be closer to the top or bottom depending on loading. Every bar has a purpose, every position has a reason. It's not decoration, it's physics. Now, you might be thinking, can't we just make concrete thicker or denser to avoid tension problems? You could, theoretically, but then structures become heavy, impractical, and uneconomical. Thick concrete slabs cost more, take longer to cure, and create additional load on foundations. Steel solves the problem elegantly without needing excessive material. It's a targeted solution, not a brute force one. Steel also allows architects and engineers to design more versatile spaces. Without reinforcement, concrete structures would need massive walls and columns, limiting open areas. With steel, floors can span longer distances, ceilings can be thinner, and buildings can be taller. Steel opens up possibilities that concrete alone simply can't. It's not about making the material better, it's about expanding what's possible with the material. Another aspect is durability. When concrete cracks under tension, steel helps keep the structure functional while repairs or maintenance are planned. It slows failure. It controls deformation. Without steel, cracks could grow unchecked, letting water and chemicals penetrate, leading to corrosion or decay. Steel doesn't prevent cracks entirely, but it buys time and stability. It manages failure gracefully. Even when you consider extreme events, earthquakes, heavy winds, or unusual loads, steel plays a critical role. It carries temporary tension spikes that concrete would instantly fail under. It allows structures to flex, absorb energy, and survive forces far beyond what concrete alone could endure.
Engineers design with these properties in mind, placing steel where it will do the most good. It's like having an invisible partner in every beam, slab, and column, silently handling the stresses that concrete can't. Now, here's a way to think about it. Steel doesn't compete with concrete. It doesn't overpower it, it complements it. Concrete provides mass, compression strength, fire resistance, durability. Steel provides flexibility, tension resistance, resilience. Together, they create a system that is far stronger and more reliable than either alone. This principle extends to construction in everyday life too. Your apartment balcony, the slab under your feet, the roof above you, all reinforced concrete. Steel is doing its job invisibly. Without it, those structures could appear fine at first, but degrade quietly over time, eventually becoming unsafe. So, the problem steel solves is not abstract, it's very real. It's the problem of forces that would tear concrete apart. It's the problem of tension, bending, and movement that occur naturally in the world. Steel quietly shoulders the load, letting concrete shine where it's strongest and keeping the structure safe and reliable. And this solves a more profound challenge too. It allows us to build bigger, taller, and more open spaces. It allows engineers to respect the natural limits of materials without sacrificing functionality. It allows structures to last decades, even centuries, while handling forces that seem invisible to the eye. That's the genius of reinforced concrete. Not magic, not brute force, not just adding more material. It's about acknowledging limitations and designing a partnership between materials. Concrete compresses, steel pulls. Each does what it does best. Each solves the problem the other can't handle. When you see a crack, you can now interpret it. It's not always a sign of failure. It's a sign that the steel inside is doing its job, quietly controlling what concrete can't. It's a lesson in balance, a lesson in understanding materials, and a lesson in solving problems elegantly. This partnership between concrete and steel is subtle, often invisible, yet fundamental. It's the reason we can span huge bridges, build high-rise buildings, and construct structures that withstand decades of weather, weight, and use. It's not just about adding strength, it's about solving the specific weakness of concrete. That's what steel really does. It solves the problem tension creates without pretending concrete can do it alone. And once you see that clearly, reinforced concrete becomes more than a construction material. It becomes a system of understanding, design, and respect for the natural strengths and limitations of the materials we rely on every day.
By now, you understand the basic story. Concrete is strong under compression, weak under tension. Steel steps in and carries the tension for it. But that raises another question. Why steel? Why not another material? Why not aluminum, plastic, carbon fiber, or even wood? The short answer is this: steel is almost perfectly suited to do the job concrete needs, and that's not by accident. Let's start with something simple. The first thing you need for a reinforcement material is that it must be able to handle tension. That's obvious. Concrete will crack if tension is applied, so whatever goes inside has to resist pulling forces. Steel is naturally strong in tension. You can pull it, bend it slightly, stretch it, and it won't fail easily. That's exactly what we need. But strength alone isn't enough. The reinforcement also has to bond with concrete. It's no good if the steel just slides inside the concrete when tension appears. Steel has a special advantage here. Most reinforcing bars are not smooth. They have ridges, bumps, or ribs. These features aren't decorative. They create a mechanical interlock between steel and concrete. So when tension tries to pull the concrete apart, the steel stays firmly in place. This interlock allows the two materials to act as a single system, sharing the load efficiently. Now let's compare steel to some other obvious candidates. Aluminum is lighter and can resist tension, sure, but it's not as stiff as steel.
It also expands and contracts at a different rate than concrete when temperatures change. That mismatch can cause cracks or separation over time. Plastic might be lightweight, corrosion-resistant, and easy to shape, but it lacks the stiffness and predictability needed for structural loads. Under tension, it stretches too much, which means the concrete around it would crack while the plastic just deforms. Carbon fiber is incredibly strong and light, but it's expensive, brittle in certain conditions, and difficult to anchor reliably in concrete on a large scale. Wood? Again, it can handle some tension, but it decays over time, absorbs moisture, and isn't predictable under varying temperatures or loads. Steel, by contrast, is just right. It's strong, stiff, durable, and predictable. Its thermal expansion rate closely matches concrete, so temperature changes don't create internal stress between the two materials. It's readily available, reasonably priced, and easy to fabricate. It's a combination of practical, mechanical, and economic reasons that makes steel the ideal choice. There's another subtle advantage that's often overlooked: ductility. Steel doesn't fail suddenly, it stretches first. That slight give is critical in real structures. It allows cracks to form slowly and prevents catastrophic collapse. Concrete alone would snap almost immediately under the same tension. Steel buys time. It gives structures resilience. You can see this principle in action everywhere. Bridges, highways, skyscrapers, parking structures, all reinforced with steel. When tension forces shift, either due to traffic, wind, or even thermal expansion, the steel is there to handle the load. If we tried to use aluminum, plastic, or wood instead, we'd see failures much sooner, or we'd have to over-design everything, making it heavier and more expensive. It's also worth noting that steel can be easily shaped, cut, and bent to fit the needs of a project. Engineers can place steel exactly where it's needed, top of slabs, bottom of beams, around columns, without the material losing its properties. Other materials either can't handle such customization or become impractically expensive when you try. Another consideration is long-term durability. Reinforced concrete structures often last decades or even over a century. The reinforcement must survive all that time without losing strength or shifting position. Steel, when properly encased in concrete, does exactly that. Concrete actually protects the steel from corrosion to some extent. Other materials might degrade faster or react unpredictably with moisture, temperature changes, or chemicals. Steel simply lasts. Economics also plays a role. Steel is abundant, relatively cheap, and standardized. Construction projects are often huge undertakings, and the cost of materials matters. Aluminum or carbon fiber could work in theory, but the price and sourcing challenges make them impractical for large-scale infrastructure. The choice of steel is also a story about simplicity. Civil engineering, at its best, finds solutions that are elegant and practical, not flashy. Reinforced concrete is a system of two materials working together. Each does what it's best at. Steel could be stronger but heavier or incompatible. It could be cheaper but weaker or less durable. It's the Goldilocks choice, just right. And here's the beauty. When steel and concrete work together, it's not obvious to anyone walking on a bridge or standing in a building. The partnership is invisible, but it's critical. The concrete seems solid and permanent. The steel is hidden inside, quietly performing the task concrete can't. Think of it this way. The system could fail if we pick the wrong material. Pick something too soft and cracks appear immediately. Pick something too rigid or incompatible and it pushes the concrete apart. Pick something too expensive or rare and building becomes impractical. Steel balances all these factors. It's not perfect, but it's close enough to ideal to allow us to build the world we know today. And the choice of steel wasn't made lightly. Engineers experimented with many materials before settling on steel. They discovered that for the forces concrete experiences, steel is reliable, predictable, and efficient. Over decades, the same principles have been validated worldwide. That's why steel reinforcement is standard everywhere you see concrete structures. Finally, steel is versatile. It can handle almost any shape, any span, any load. Reinforced concrete is modular in concept. You can combine concrete and steel in countless ways: slabs, beams, columns, walls, shells, while still relying on the same basic principles. No other material offers that combination of flexibility, strength, durability, and practicality. So when you see steel bars embedded in concrete, don't just think of them as extra material. Think of them as the precise solution to a specific problem, the problem of tension that concrete alone cannot resist. That's what makes them essential. That's why engineers insist on them. And that's why buildings, bridges, and every reinforced concrete structure you walk past are safe, functional, and long-lasting. In short, steel was chosen because it fits the problem perfectly. It handles tension, it works with concrete under varying temperatures, it lasts decades, it can be shaped to the design, and it's economically viable. Nothing else comes close. Steel isn't just a choice, it's the solution concrete needs to perform in the real world. And once you see this clearly, you start appreciating the elegance of reinforced concrete. It's not brute force, it's not overcomplicated, it's a partnership. Concrete handles compression, steel handles tension. Each does what it's best at, and together they create something far more reliable than either could achieve alone. That's why we use steel, not because concrete is weak overall, but because it's weak in a way that matters, and steel solves that problem perfectly.
Imagine a world where concrete is poured without steel reinforcement. It looks the same on the surface: solid, gray, heavy. It might even stand up for a little while, especially if the span is short, the loads are light, and everything is perfectly balanced. But look closer. Forces are everywhere. Gravity presses down. People walk. Cars drive. Wind blows. Temperatures change. All of these forces create tension inside the concrete. And concrete, as we've already seen, hates tension. Without steel to handle that tension, cracks start to form. At first, they're tiny, almost invisible. A hairline across a floor slab, a small fissure at the bottom of a beam. No one notices yet. The structure still seems solid. But those cracks are warnings. Small, yes, but meaningful. Time passes and the cracks grow. Repeated loads, thermal expansion and contraction, even minor vibrations make the fissures widen. Water starts to seep in. Moisture carries chemicals that react with the concrete. Freeze and thaw cycles make the cracks expand and contract. Without steel, the concrete has no backup. Nothing absorbs the tension forces. Nothing distributes the load. Cracks grow unchecked. Eventually, they connect, forming larger fissures. At this point, the concrete might still be standing, but it is no longer reliable. Now, imagine a concrete beam spanning across a room designed without steel. People walk on the floor above. Furniture, machines, or even a heavy vehicle passes overhead. The bottom of that beam is under tension, stretching more than the concrete can handle. A crack forms, and another. Soon, the cracks link together. What happens next depends on many factors: load, span, quality of concrete, environment. But the outcome is inevitable: failure. Concrete will fracture, sometimes suddenly, sometimes gradually. A floor may sag, a ceiling may drop plaster or even collapse. Walls may crack open. Bridges could fail under the weight of traffic. Even if the concrete looks strong, the forces inside never lie. Without steel, concrete alone cannot manage tension. It's like asking a runner to carry a weight far beyond what their muscles can handle. The effort fails, no matter how solid the runner looks. And it's not just the cracks that are dangerous. concrete shrinks as it cures and expands and contracts with temperature. Without steel, those movements create more tension in vulnerable areas. Shrinkage cracks appear during curing. Thermal cracks appear with the seasons. None of this would be catastrophic if the structure had reinforcement, but without steel, these minor issues can quickly escalate. Let's take a real-world example. Imagine a simple concrete slab for a parking garage poured without steel. Cars drive over it daily. Temperature changes cause expansion and contraction. The bottom of the slab is under tension. Micro cracks form. Over months and years, water penetrates. Reactions occur inside the concrete, weakening it further. Eventually, the slab can no longer carry the loads. Sudden failure occurs, possibly catastrophic. It doesn't take extreme conditions for concrete to fail without steel. Even modest tension over time is enough. The forces might be invisible to us, but the concrete feels them every day. There are historical examples too. Early concrete structures built without steel reinforcement lasted a few years or decades, but many eventually cracked, sagged, or failed entirely. Engineers learned the hard way that compression strength alone is not enough for real-world structures. They realized that without a material to handle tension, concrete's potential is limited. In short, the problem without steel is not immediate collapse in every case. It's unpredictable failure. It's hidden weakness. It's a structure that may look fine until one day, under the wrong combination of forces, it fails. This is why reinforced concrete is so critical. Steel doesn't just make concrete stronger, it ensures that the structure can withstand forces that concrete alone could never survive. Without it, engineers are gambling with hidden tension forces. Even small spans can fail. Even seemingly insignificant loads can create tension zones that crack concrete. And once cracks start, everything becomes cumulative. Concrete has no memory of where it was weak, but cracks remember. They grow, connect, and eventually destroy the reliability of the structure. Now, consider the human aspect. If engineers ignore reinforcement, lives are at risk. Buildings may sag, floors may collapse, bridges may fail. The damage isn't theoretical. People could be injured or killed. The invisible problem, tension, becomes very visible in a catastrophic way. So what exactly is steel solving? It's taking the tension forces that concrete cannot handle and managing them efficiently. It prevents small cracks from growing uncontrollably. It distributes stress over larger areas. It allows the structure to flex, move, and survive in the real world. Without steel, all of that disappears. You can almost imagine the concrete crying out for help without its steel companion. All that compression strength, all that solidity is wasted under tension. It's strong in the wrong places, weak where it matters. Steel is more than a safety measure. It's the difference between a building that lasts decades and one that fails quietly. It's the difference between a bridge that carries thousands of vehicles safely and one that develops hidden cracks until it's too late. It's not decoration, it's not optional, it's essential. And the lesson goes beyond construction. It's a reminder that even the strongest materials have weaknesses. Ignoring those weaknesses can lead to failure. Addressing them intelligently, placing steel where it's needed, creates stability, resilience, and reliability. So, the next time you walk on a concrete floor or cross a bridge, remember, what you see is not the full story. The concrete is carrying compression. The steel is carrying tension. Together, they solve a problem that neither could handle alone. Without steel, concrete would eventually fail under forces it simply cannot resist. It would crack, sag, and potentially collapse. Steel isn't just reinforcement. It's a carefully chosen solution to a very real problem. It's the hidden hero of modern construction. And that's why no engineer in their right mind would ever skip it.
By now, we've gone through concrete, steel, and why they work together so well. But here's something I find fascinating. This isn't just a lesson about materials. It's a lesson about people, teams, and how we approach challenges in real life. Think about it. Concrete and steel,
two very different materials, one strong in compression, the other strong in tension, one brittle in certain situations, the other flexible. Each has limitations, but when they come together, they create something far more reliable than either could achieve alone. Now, replace concrete with a person who's exceptionally diligent, meticulous, and stable. They're strong under pressure, consistent, dependable, but maybe they struggle with flexibility, adapting to unexpected challenges or thinking on their feet. That's their tension weakness. Then imagine a colleague or teammate who is adaptable, creative, and excels under unpredictable circumstances. They are strong in tension in human terms. They can absorb surprises, stretch to meet challenges, and manage situations others can't. But maybe they struggle with consistency, structure, or routine. That's their compression weakness. Put these two together, just like steel and concrete. Each does what they are best at. The reliable, structured person handles the foundation, the bulk of the work that requires stability and predictability. The flexible, adaptable person handles the unexpected, the tension that arises when challenges try to pull the project apart. Together, they create a system that is balanced, resilient, and capable of much more than either alone. It's the same principle in teams. In any project, forces are at play. Deadlines, client expectations, unforeseen problems. These forces are like tension on concrete, invisible until they cause cracks. If the team is made entirely of concrete types who are great under predictable conditions but struggle when stretched, cracks will appear. Stress builds, morale dips, communication breaks down. If the team is entirely steel types, constantly flexible but lacking structure, the project may bend and twist but never solidify, never achieve stability. The magic happens when you combine strengths. Teams work best when people cover each other's weaknesses. Some provide the solid foundation, others provide the flexibility to handle unexpected stress. When this happens, projects survive pressures, adapt to changes, and deliver results efficiently. It also applies to leadership. A good leader is like the engineer who knows where to place the steel. They recognize the strengths and weaknesses of their team, understand the forces at play, and create a structure where each person can perform where they are strongest. The leader ensures that tension in the team, stress, conflict, unexpected challenges, is managed effectively by the right people. The leader doesn't try to make everyone perfect in every way. They design the team like reinforced concrete, positioning strengths to cover weaknesses. In life, we encounter similar dynamics with friends, partners, and collaborators. No one is perfect in every dimension. You can't be strong in every situation, stable under all conditions, flexible under all circumstances. The key is finding people whose strengths complement yours. When you collaborate thoughtfully, you create a system more capable, more resilient, and more enduring than the sum of its parts. Here's another parallel. Just like steel placement in concrete isn't random, collaboration isn't accidental. The right person in the right role makes all the difference. You wouldn't place a creative problem solver in charge of routine, repetitive tasks any more than you'd place a concrete-only beam where tension is expected. Understanding the forces at play, tasks, pressures, deadlines, challenges, is essential. Then assign responsibilities where strengths can truly shine. There's also the matter of visibility. In reinforced concrete, steel is hidden inside. Most people don't notice it. It quietly handles the tension forces without fanfare. In teams, the same is true. The person managing conflict, smoothing communication, solving unpredictable problems may not always get recognition. They are the hidden steel, essential to the integrity of the project, but not always visible. And just like in construction, underestimating or removing that person can have serious consequences. The combination of complementary strengths also builds resilience. Just as reinforced concrete survives decades of stress, change, and use,
Teams built on complementary strengths survive challenges that might break less balanced groups. Cracks will appear, stress will happen, but if the right people are in place, the cracks don't spread uncontrollably. The system absorbs, adapts, and continues. Another lesson is humility. Concrete doesn't pretend to resist tension. Steel doesn't pretend to resist compression alone. Neither is perfect on its own. Similarly, people and teams perform best when they recognize limitations. Pretending to be strong in all areas rarely works. Understanding where you were weak and where you were strong and seeking collaboration to balance those forces is not a sign of weakness. It's a sign of intelligence and practical foresight. And this goes beyond work. In friendships, partnerships, families, even communities, complementary strengths create harmony. Someone provides stability, another adaptability. One plans and organizes, another improvises and innovates. Each covers the other's limitations, just like steel and concrete covering each other's weaknesses. Without that balance, systems fail, whether a structure collapses or a relationship struggles under tension. The final point is about foresight and design. Engineers don't wait for concrete to crack before adding steel. They know where tension will appear and place reinforcement proactively. In teams and life, the same principle applies. Anticipate where challenges will arise, identify potential weaknesses, and position people, friends, colleagues, collaborators, to absorb the pressure. Don't wait for failure to teach the lesson. Build complementary systems from the start. So, the lesson of steel and concrete isn't just about construction. It's about understanding natural strengths and weaknesses, designing systems where strengths compensate for weaknesses, and building resilient, adaptable structures, whether in buildings, teams, or personal relationships. When you step back, reinforced concrete becomes more than a construction material. It becomes a metaphor for human collaboration. Recognize what you do well. Recognize what you struggle with. Partner with those whose strengths complement yours. Position everyone thoughtfully, like steel and concrete. Expect challenges, absorb stress, and manage tension. And remember, the strongest systems are rarely the ones where one person does everything. They're the ones where different strengths work together, each handling what the other cannot. So the next time you walk across a bridge, stand on a high-rise floor, or just work in a team, think about steel and concrete. Think about tension and compression, cracks and reinforcement, and think about how complementary strengths, whether in materials or people, create something far stronger than any single element alone. The concrete carries the weight, the steel absorbs the pull. Together, they endure. And in life, it works the same way.
So let's take a step back and look at the bigger picture. Concrete and steel, two very different materials. One is rigid, solid, and strong under pressure. The other is flexible, resilient, and strong under tension. Each has its own limitations. Alone, they can't handle all the forces a structure faces. Together, they create something far stronger, far more reliable, far more enduring than either could achieve on its own. That partnership is the core lesson. It's not about brute force. It's not about adding more material or trying to make one thing do everything. It's about understanding limitations and designing solutions that respect those limits. Concrete carries compression. Steel carries tension. Simple, elegant, effective. And the fascinating part is how much this principle applies beyond construction. Think about people, teams, and life itself. Each of us has strengths and weaknesses. None of us can do everything perfectly. Some of us excel under pressure, others excel under uncertainty. Some are great at routine, some at improvisation. Alone, we face limits. Together, complementary strengths allow us to handle challenges that would overwhelm any one person. The steel and concrete analogy is a perfect reminder. The right collaboration is not accidental. Position the strengths where they are needed. Recognize where weaknesses will appear. Support one another. Let each element do what it's best at. That's how resilience is built, whether in buildings or in life. And just like reinforced concrete, the strongest systems are often the ones where the most critical work happens quietly. You might not see the steel inside a beam, but it's doing the job that keeps everything above it safe. In the same way, in teams and relationships, the most important contributions are sometimes invisible. Recognize them and respect them. Finally, remember that balance is key. Overemphasize one strength, ignore the weaknesses, and cracks appear. Sometimes gradually, sometimes suddenly. A system that respects the natural capacities of its parts, that positions each strength strategically, is not just functional, it's resilient, elegant, and enduring. So next time you walk across a bridge, enter a building, or just work with people, think about steel and concrete. Notice the balance. Notice the collaboration. Notice how understanding limits and complementing strengths create structures and teams that last. Concrete and steel, people and teams, pressure and tension. Life is full of forces, visible and invisible. The lesson is simple. Know your strengths, know your weaknesses, and build the right partnerships. That's how stability, resilience, and real strength are created. In the end, it's not just engineering, it's a way of seeing the world, a reminder that no one stands alone, and no material, no person is meant to do it all. Together, with the right balance, we endure.